Thank you, Josep, and again for your presentation. We move forward with the following presentation, which will be given by Floris Laporte from the University of Gent.
Hello everyone, I'm Floris. I'm from the Photonics research group at Gent University, and today I'll talk about photonic reservoir computing, which is a form of photonic neuromorphic computing. And in particularly, I'll show how this photonic reservoir computing can be used for telecom applications. So the main goal of this talk is not to present you with the biggest chip with the most amount of nodes possible, but to have a slightly smaller chip with a limited number of nodes, but which can still do particularly interesting things, especially at very high speeds for telecom applications. So, yeah, this is basically. I would like to start the presentation with like the black box principle, like we would like to call it. So, for example, this kind of chip. This is kind of an old chip we made like 5 years ago or so. And the question is, what can this chip do? It's basically the idea of neuromorphic computing. It can do a lot of things as long as you train it for this particular for a particular purpose. So, for example, this specific chip can do several telecom-related tasks, such as bit manipulation, up to 5-bit header recognition, nonlinear signal equalization, and actually many more tasks. And the idea behind this is that this is with an as low as possible number of active elements on the chip to make it very easily scalable to very high speeds. So that's the main idea of what we are trying to do in our group. So we're trying to basically make a multi-purpose chip for optical computing and for telecom applications. So this black box computing is often called reservoir computing. And it's basically coming from the idea of neural networks. I think Bert this morning gave a very nice introduction of neural networks. I'll do a very short recap of this. So imagine, for example, the feed-forward kind that was introduced this morning, where you have several nodes connected in one direction from one side to the other. In general, these nodes are interconnected by weights, or in our brain they're called synapses, but we basically optimize these weights for a particular purpose, and they are optimized with an algorithm called backpropagation, so that after the optimization, the training basically of your network, you basically can do some interesting tasks, for example, image recognition or whatever. However, this is not the complete story, because when you're working with telecom signals, you would like to have some kind of memory in your system, because your telecom signals are inherently time dependent. So you basically need some kind of feedback in your neural network. And this makes training of your weights a lot more difficult. And in software, there are several ways to work around this and to make it better. But back in the beginning of neural networks, they had a very smart solution to this, which is basically don't optimize it. And basically, they just use a very large, or they use a recurrent system to basically transform your signal and then read out this reservoir state with a readout layer, what they call it. So this readout layer is optimized, the rest of the network is not. And the reason that this works is because basically your reservoir transforms your time-dependent input signal, which is in telecom very often low dimensional, to a higher dimensional reservoir state. And the idea is that when you transform this to a higher dimension, your signal becomes linearly separable in this idea, in this problem. So you can find a linear readout layer for each purpose of your chip. And this linear readout layer can then easily be implemented in the hardware. So basically, this brings us to basically two core principles of reservoir computing. You have this transformation to a higher dimension, and you need some memory in the system, so you need some recurrency in your system. So that's basically, if this is all you need, you're basically not very interested in what happens in your reservoir. So basically, you can really regard it as a black box. That's why we often call it the black box principle. And the prime principle, or the prime example that we usually give is, for example, in the beginning that reservoir computing was being used, there were a lot of people trying to find the most original reservoir, I think. So one of the examples is doing reservoir computing with a bucket of water, where they do speech recognition by looking at the ripples in the water that exist in the water. So yeah, you can see it as broad as you want in reservoir computing, as long as your system basically is rich enough to do some kind of interesting things. So that's an idea that we want to use in photonics, which brings us to photonic reservoir computing. And the most straightforward way to implement this is, for example, to basically use some kind of recurrent system on a photonic integrated chip. So that brings us to the chip that I introduced in the beginning of this talk. The idea is, you can basically make these nodes several ways. You can use semiconductor optical amplifiers, which are quite nonlinear, so that's quite interesting. However, they use a lot of power. Not that much power, but if you use a lot of nodes, it will quickly raise the power consumption of your chip. Or you can use some kind of other system like excitable ring resonators. And although these systems kind of work, what we are trying to do in telecom is basically have a very fast chip that uses as little as possible power. So what we figured out is that actually you don't need much nonlinearity for the tasks that we want to tackle. And basically using just passive splitters and combiners is often enough for some basic tasks that we want to do. And this works because you have, obviously you have an amplitude and a phase, and you have interference in your chip. And when you detect your signal, you still have a nonlinear operation. And this nonlinear operation at the end, at the detector, is basically often enough for a lot of telecom applications. So that brings us to the passive photonic silicon reservoir, which basically is a giant multipath interferometer, and the nodes are simple splitters and combiners, and nonlinearity in the readout suffices. And the cool thing about this is that there's actually no active power consumption on your chip, and you're also not limited by the time scale of the nodes in your chip, so you can make it really fast and low without much power consumption. So this is one of the first results we had a few years back, I think in 2014, I think, where we showed some header recognition performances up to 5-bit header recognition, or up to at least 3 to 4 bits header recognition, and also some temporal bit manipulations, just like AND and XOR task. Quite simple tasks, but if you can do them at high speed, they're quite useful. And it's important to note these speeds here are not very fast, but they were artificially limited by having very long delay lines between the nodes. So I think we used 3-centimeter delay lines between the nodes to reduce the speed of the chip. So by reducing the length of these delay lines, you can basically reach arbitrary high operation speeds. So the drawbacks of this is, of course, photonics is generally, of these kind of integrated photonics, is you have a large chip footprint. You have a quite limited interconnection topology because you're still working with a 2D structure. If you compare that to software neural networks, for example, each node is connected to any other node. here you're basically only connected to your neighbors, so that's still a little bit of a drawback. You have a limited number of nodes. I think this first incarnation of chips had 60 nodes. That's not much, especially if you want to tackle some more interesting tasks. And this first incarnation also had like a lot of 3D splitters and 3dB splitters and combiners, which reduced the power efficiency of this thing. So, and also the readout was still implemented electronically. So these problems can be tackled. The first things that we try to do is increase the number of nodes and switch out the interconnections, the nodes basically, from 3dB splitters and combiners to more reversible structures like directional couplers or MZIs. And this gave rise to a 32-node structure that we're working on in the Fresco project, with shorter interdelays, which aims at operating range of 32 gigabits per second, and with an integrated readout. So basically, this kind of structure ideally tries to do everything optically. It has 7 optical readouts, so it basically reads out 7 of the reservoir nodes and tries to do the weighting operation in the optical domain as well, so that everything can go really fast. However, we also did some other what we call hybrid readouts, basically readouts that rely on photodetectors and which you can still weigh in an electronic circuit, because the optical readout is still not very reliable so far. So this kind of new design solves already a few of the problems. It increases the number of nodes, but I think we can all agree that 32 nodes is not that much still. It also reduces the losses in the reservoir, and it tries to implement an integrated readout. And so I'll go a little bit deeper into this integrated readout. So generally speaking, what you would do is for each node that you read out in the reservoir, you would need a separate photodetector. And if you increase the number of nodes, you need a lot of photodetectors, which very much complicates your circuit, because you need analog to digital converters for each of these photodetectors, and then you need to combine them in the electrical domain. So ideally, and that's what we tried with 7 of these nodes, you would have an optical weighting mechanism that's basically based on heaters or another optically active material, so that your weighting can happen in the optical domain, and then you just need one photodetector at the very end to basically use your signal, or even better, no photodetector and just connect it into your link, maybe an amplifier at the end. That would be even better in that case. So on this chip, visualized in the corner there, we basically still used heaters, but we are also looking together with IBM, I think, into optically non-volatile materials, so you don't have to use these heaters. The drawbacks of these non-volatile materials is that you have less bit levels, basically. You have less levels available for your weights, so that means you have a very coarse-grained weighting mechanism. It's also something that we've been looking into theoretically, how you can train these weights in a better way. And it turns out, actually, like the 20 levels that you have for these BTO-based weighting levels should be enough for almost the same performance as infinite precision weights. So that's good news. That's some new results that we have submitted to TNLS. But also, this kind of new chip, if you would just go back to the electronic weighting, it also allows for some more interesting tasks, because the losses are lower, so you can do more interesting tasks than just bit manipulations. So one of the tasks that we're trying to tackle is nonlinear signal equalization or nonlinear distortion in a long optical fiber. So basically you have an optical signal going through your optical fiber, which gets distorted. The traditional way to handle this would be to use an analog to digital converter, and then process your signal in the digital domain by a DSP, digital signal processor, and then convert that signal back to the optical domain, which is, of course has two electro-optical conversions, once to the electrical domain and then back to the optical domain, which is power inefficient. These DSPs are also quite expensive, so ideally we would like to have this in a purely optical way, so that's basically where this chip comes in, and which basically also is very fast. So this is some of the tasks that we've been trying to solve. You have, we did 25 kilometer fiber, which is of course not very much, but at least you see some improvement in the eye diagrams here. So for example, if you compare to a simple tapped filter design versus our reservoir chip, you see that the eye diagrams for this reservoir are better. We also have no errors in 2 to the 15 bits for this kind of problem, while the tapped filter averages out at 1 error in 100, 10 to the minus 2. So this is a quite interesting result. However, this design, as interesting as it is so far, it's still quite big. It has a large footprint on your chip. It still has this limited interconnection topology. It doesn't do anything better than the previous generation of our chip. It has a limited number of nodes. Still, 32 nodes is still not that much. So basically, maybe we should have a look at some alternative reservoirs. And for this, it's interesting to remember the bucket of water that I talked about in the beginning of this presentation. Maybe we can make some kind of photonic equivalent for this bucket of water, which, for example, is a photonic crystal cavity. So we've done some simulations with this, where you send in light along one of the arms, and then instead of looking at the field profiles, because obviously you don't have the resolving power to look at the field profiles, you look basically at the light leaking out of this cavity. And this basically works like any other reservoir computing approach. You send in light at a high bit rate, and you look at the distorted light coming out, and then you use a weighting mechanism at any of the arms to create your linear combination of your reservoir states. And this is the advantage, that you can use much smaller chip real estate. So for example, this is a 30 by 60 micrometer cavity, which is a lot smaller than the few millimeter by millimeter cavities or reservoirs that we were talking about earlier. And even you can make this cavity as small as you like, as long as you can attach enough waveguides in there. So for example, we went to a theoretical 2 terabits per second if you would reduce it to 5 to 6 micrometers. So the speed is not a problem. Obviously, you're limited by your detector then. These are speeds that you cannot reach. So we made such a cavity. And I'll show you some results about this later. But the main idea here is that these photonic crystal cavities, they are quite interesting in theory in our simulations. But if you want to mass integrate these, they are very difficult to make. So we also made some more easily fabricatable cavities, which are basically just based on index contrast by making a trench around the silicon slab. They are obviously way more lossy than the photonic crystal cavities, but they seem to work good enough for the applications that we're targeting. Remember, you need to have some memory in your reservoir, so as long as you have like basically 2-bit memories, you can already do some operations on 2 subsequent bits or whatever. So that's what we've been targeting with these kind of cavities, which are very easily to fabricate. And the idea is, these cavities, if you remember the definition for this reservoir approach, they transform your signal to a higher dimension. So you have 1 input signal, you have 6 output signal, signals, and they exhibit the memory. So if you, for example, send in a 20 picosecond pulse, you see that the output arms, that the output pulse response basically is much longer than this 20 picoseconds. So you see that it has a memory. So ideally, you would have some interesting mixing. And that's what you also see here. You have a 1D input coming into your signal, and then you have a 6D output. And by using some, like 6Ds, 6 dimensions are hard to visualize. So by using some kind of projecting on 3 dimensions, for example, by principal component analysis or something, you see that automatically you get some clustering in your things, in your bits. So basically, different bit sequences will end up in different locations in this thing, which makes it very easy to find a linear classifier for your problem. So that's basically this abstract idea of transformation to a higher dimension in action. It's much more easy to find a linear classifier for the problem you have there. So what can you do with this kind of cavities? We basically apply the same kind of benchmark tasks to them. So like the XOR task is available on a high range of bit rates, at least in simulation. If you look at the measurements, these are still unpublished results, but if you look at the measurements, the operating range is a lot less wide, but at least we have some working cavities that show promise in this regard. Same here, if you reduce the cavity in simulation, you can reach up to 2 terabits per second operation. The blue line here is, for example, an 18 micrometer cavity by 13 micrometer, or the orange line is a 6 by 5 micrometer cavity. You can also do header recognition with these tasks, with these cavities, where you see that in simulation we have a very wide range of operation as well for up to 6-bit headers. And in measurements, of course, a little bit less good. But at least for any of the cavities that we've tried, we find operating ranges that work, and they're very fast. As you can see here, we can reach up to 50 gigabits per second almost header recognition in real time. So that's quite interesting. So to conclude, I showed you some reservoirs that we're working on in our research group. First, I showed you some improved reservoir designs, which used improved nodes and make different kind of tasks available to us. So, for example, the nonlinear distortion compensation and so on. And I also showed you an alternative cavity-based reservoir, which I think is also very interesting to look into, because actually when you're working with photonics, you should not be limited to this node-based structure, because light is inherently parallel and light scatters around, and if you can use this richness, it gives quite interesting effects. And also we looked into using a readout, integrated readout, which on the current chip is still using heaters, but we're looking into non-volatile weights there as well. So that's it for my presentation. Thank you very much.
Questions from the audience?
Yeah, thank you for the presentation. It was very insightful. So what is the guiding principle for designing the reservoir cavities? How do you start the design process?
That's a good question. It's a lot of trial and error. Basically the idea is that you use kind of a shape that is known for interesting mixing dynamics. Basically, for example, this kind of shape that you've seen is known as a quadrostadium shape. I'll show you the cavity again. Here maybe. It's known as a quadrostadium shape. It's known in microwave optics, for example, to have almost chaotic mixing, and because of the losses in your in the cavity, you will have some fading memory, which is also interesting. So you will have a very good mixing of your input signals. So this is basically the guiding principle. To know which bit rates to target is a more difficult task. That's basically something that you do by measuring it, because the simulations are not, as you see, the simulations are not as accurate as we would like to. But yeah, that's basically a bit try and error.
Last question.
Maybe related to that question, you mentioned here that you have 6 dimensions because you have the 6 outputs.
Yeah, but that's, yeah.
I mean, maybe 2 outputs represent the same dimension.
Yeah, there could be they're definitely in some sense linearly dependent, because you don't have really 6 orthogonal dimensions anyway. So there's some linear dependence in between them, and you also see that if you reduce the number of arms, that you still have some performance. But if you, we did some tests with like varying number of arms, and you see that increasing the number of arms really improves the performance up to a point, and then it stops. So it's also, yeah, you definitely, they're not orthogonal in a
okay, but at least to some extent.
To some extent, they represent different,
okay.
different ways.
Yeah, thanks.
Thank you, Floris, for your presentation.
Thank you.